In today's lesson, we're going to examine some other places we can create models, in particular the world of economics, finance, money. And it's kind of a big idea in economics is you want to figure out your optimal something, your optimal number of sales you should make, the optimal amount of money you can make, what's the most amount of revenue, the least amount of profit, things like that, right? They're all optimizing problems. So just some words we're going to come across just to point out to you. The word marginal in economics, marginal, refers to rate of change. So if I'm talking about my marginal cost, I want to know how my cost of change, sorry, my rate of change, how my cost is changing. If I want to talk about my marginal revenue, how's my revenue changing? And marginal profit, how profit's changing. And don't forget the profit is always your revenue minus your costs. You don't actually get every penny back that you sell something for. It probably cost you something in the first place to make it. So we're going to start off with a simple one. They're going to have a model they're going to give us here. So example one, the cost function for producing X number of items is given by this lovely equation. And I want to figure out the average cost of producing 150 items. Well, average cost isn't really calculus. Average cost is, well, how much did it cost us and how much is each one? Okay, think about any other average. We take our total and divide by the number of things, and you get your average mark. You add up your tests and divide by how many you took, right? So same idea here. If I want to figure out my average cost, I'm going to have to figure out the cost for 150 things, which is just using that original equation, and divide it by how many things I made. So if you use our equation and replace all the x's with 150, so like 0.00013 times 150 cubed minus 0.002 times 150 squared plus 5 times 150 plus 2200, all divided by 150. I'm just using our calculators here. Hopefully on the top you get something like, I think this is right, 3343.75. That's how much all 150 items cost to build or make. And there's 150 of them, so each one would cost you roughly $22.29. Okay, part B, find the marginal cost. There's that word for us, marginal. That means find the rate of change of costs. In other words, find your derivative. So for part B, we're going to take the derivative of our function. Just be careful with your decimals here. We're just using our good old power rule. So 0.0013 times 3 will give us 0.00039x squared. And we do the next one, we should get minus 0.004x squared and 5. And this whole thing, this expression is called our marginal cost equation. The cost, the rate of change of producing items. Okay, part C, 150. Okay, so part C, I want to figure out the derivative at 150 and then explain what it means. So I'm going to replace all my x's with 150. Actually, you know what? That's not a squared anymore. Sorry, guys. That should just be the letter x, right? 150 and then plus 5. And we put that in our calculator and we end up with 13.18. And what does that represent? That represents the cost of producing the next item. Okay, so this is the cost of producing the 150th item. And it's a rough estimate. The rate of change at 150 is the estimate of what it costs to actually do the 150th item. In part D, they're asking us to figure out the actual cost of the 150th item. So to figure that out, I can take how much it costs to produce 150 items, but remember that's all 150 items, and subtract what it costs to produce 149 items, again, all 149 items, and the difference between those would be the cost of the 150th. Okay, the difference between any two items is what it actually costs to produce that single item. So if we go back to our original equation, we already figured out 150 items was this number, right? 3343.75. So 3343.75. If we put 149 into our equation, you should get 3330.63. Now if I subtract those, I end up with $13.12. So based on my model, I thought the cost of producing the next item should be $13.18. It turns out it's actually only $13.12. That's the whole idea of calculus, is we can use it to estimate what's happening at points. Okay. Okay, so let's take a look at another example. So an electronics store is selling personal MP3 players. The price for each CD player is $90. I should say MP3 player. During a typical 2 weeks, the store sells 50 units. Past sales indicate for every $1 decrease in price, the store sells 5 more units in 2 weeks. Calculate the price that maximizes revenue. This is actually a sort of a grade 10 style question, a quadratics one. You might remember that when we want to find revenue for one of these things, we always took the number of items times their price. So how many items do we usually sell? We usually sell 50, but that can change. Every time we decrease our price, we actually sell 5 more units. So it goes up 5 for every time I change my price. X is the changes in price. Okay, that's how, or sorry, changes, yeah, changes. Our price, what happens to our price? Well, we normally sell it for $90, but we might decrease that to increase our sales. We're going to decrease it $1 each time. And this will give us sort of a expression for our revenue. Now, I want to maximize this revenue. In other words, I want to take my derivative and set it equal to 0. But the format I'm in isn't great for doing derivatives. Let's expand and rearrange. So if we expand, we do our FOIL, 4,500 minus 50x plus 450x minus 5x squared, or in other words, put in the right order, negative 5x squared, 400x, and 4,500, I get an expression for revenue in terms of how many times I should change my price. My maximum will occur where my derivative equals 0, our optimal situation. Derivative is negative 10x plus 400, or 10x equals 400, or x equals 4d. So what should I do? I should change my price. Remember, x was number of changes. So what was our question? The question was, what price maximizes revenue? Our price was given by 90 minus 1x. And we said our maximum revenue happens when we change our x to 40. Change our price 40 times. So 90 minus 40, we should charge 50 bucks. That will maximize our revenue based on this idea of for every decrease in price, I sell 5 more items. Okay, if we try the third one, market research indicates a computer company that manufactures something, laptops, will sell at a price of 2,000 minus 5x. That's x thousand units. The cost to produce this many units is given by this. Determine the level of sales that will maximize our profits. So here, we got to think about profit. How do I find profit? Well, I bring money in, my revenues, whatever I sell them for, and I still got some costs actually to produce these things. So what do we know about our revenue? We know we bring in 2,000 minus 5x. That's our revenue for every one that we sell. Actually, sorry, for every 1,000 that we sell. So how much money do we actually bring in? We bring in 1,000 times 2,000 minus 5x, right? It's 2,000 minus 5x per unit. 1,000 units, x thousand units. So we're going to multiply those two things together. Oops, I missed a number there. X thousand, 1,000x. Sorry. Our costs, we were told, was 15 million, 123, plus 1.8 million, plus 75x squared. Okay. So the tricky part here in this one is that our revenue is made up of how much you get per unit and how many units we actually sell. X thousand units. So your money you're going to make will be the number of thousands of units you have times the per unit value of those, right? Now, obviously, we want to maximize the profits. We want to take a revenue, but we're definitely not in a good format to take our derivative at this point. So let's simplify. Expand our brackets. And 5,000 x squared. We're going to deal with all our signs over here, right? The negative sign in front. So 15 million and 1.8 million and minus 75x squared. And let's collect our like terms. We should get 5,075x squared. We should get, I think it's 2 million x. And at the end, we should get 1, 5, 1, 2, 3, 1, 2, 3. Just let me check my zeros on the previous number. 1, 2, 3. Oh, I got 120 zeros there. Right. Okay, there's an expression for our profit in terms of how many units we sell. We want to maximize our profit, so our derivative equal to 0. Let's do our derivative. 2 times 5,075 is 10,150. And then we just get rid of the x part. 1, 2, 3. We want to solve that. So 10,150x equals 200,000. And x comes out to 19.7. Remember, x was x thousands of units, right? So we actually sell 19.7 thousand units. So sales of 19.7 thousand units will maximize profits. Okay, and one last one. Sandy's making a box, a closed rectangular box with a square base from 2 different woods. Okay, so we have a square base. Square. Make it look real square here. And we're using 2 different woods. The wood for the top and bottom costs $20 per meter squared. The sides cost $30 per meter squared. Find the dimensions that will minimize the cost of the wood for a volume of 4,000. So if it's a square, then I know this is x and this is x. I don't know how long this box is or how tall this box is. We'll call that our height. But I know I can find volume by doing length, width, and height. And I've been told the volume is 4,000. So we can do what we've always done and say, well, 4,000 equals x squared h. Again, I'm thinking about this idea. I've got 2 variables. I'm probably going to want to simplify that. That's what I've always done. And I got my expression for my height. Now this question wants us to minimize the cost. The cost means I actually have to build this box. In other words, I need to know the surface area. So my surface area of my box is I've got a top and a bottom, and they're each x squared. And then I've got 4 sides, and they're each x plus h. Now, hang on a second here. 2 top and bottom plus 4 sides are each x plus h. So my surface area is really 2x squared plus 4x h. So we know about h from up here that we can replace h with 4,000 over x squared. And if we simplify that, we'll end up with 2x squared plus 16,000 over x. That's an expression for our surface area. Again, our question isn't about surface area, though. It's about cost. We're trying to minimize our costs. So our cost, what do we know about our costs? For the top and the bottom, it costs $20 per meter squared. Well, the top and the bottom is this piece. So I need $20 for every meter squared of use of that. Plus, I need $30. It was 30, wasn't it? Yeah, $30 for every piece of this. I'm going to bring the exponent up, okay, of that. So my cost equation is actually 40x squared plus 480,000 x to the negative 1. There's an expression for our cost. Cost we want to minimize. How do we minimize it? Derivative equal to 0. So 0 equals 80x squared plus, oops, not plus, minus 480,000 over x squared. And we're going to do our standard cross multiply and solve, right? How do I get x squared in there? Sorry, guys. That shouldn't be a squared there, just an 80x. Okay, so 480,000 equals 80x cubed. Divide out the 80 from both sides, and we'll get 6,000. Take our cube root of 6,000, and for x we should get, do it right, 18.17. Okay. And for our height, because it asked us for the dimensions, we go way back up to the top. We said that height was 4,000 over x squared. So if I want to do my height, 4,000 over x, x is 18.17 squared, and we will get 12.11. Okay, so therefore, the dimensions to minimize cost are 18.17 for your base, so it's 18.17 a square, right? And the height of 12.11 centimeters. Okay.